Hello and welcome. In this video, we're going to look at how to calculate parallel LC resonant frequency when we're neglecting winding resistance. So typically, when we want to solve for this, we don't neglect winding resistance, and that makes the equation quite a bit larger. So we have our frequency equation, FR, for our resonance frequency, is equal to the square root of 1 minus our winding resistance, RW squared, times our capacitor divided by our inductor, and that evaluates all three of those together. Then we divide that entire thing by 2 pi square root LC. And so this top half evaluates the impact of the winding resistance on the capacitor and inductors and compares it to the square root of 1. And so that is going to basically subtract from 1. And on the bottom it says that 2 pi, that's a rotation of a circle. And then our time constant for our LC is at the end here. So if we want to eliminate winding resistance, we'll eliminate the top half here and replace a 1 with it instead. So our frequency equation that we're going to use for this one is 1 over 2 pi square root LC. So we're just going to replace that top with a 1 to neglect winding resistance. And on the bottom, we'll say that we are rotating around a circle, and this is our time constant for the speed that we're rotating at. And that 1 on top gives us our frequency instead of our time. So if we didn't have that inversion, you'd have a really small time value instead of a frequency value. So let's plug that in. So we'll say that we have 1 over 2 pi square root of our inductor, which is 0.56 millihenries, multiplied by 0.062 microfarads. We're going to plug those variables in there to our calculator. 1 over 2 pi square root of millihenries here. So we can move that decimal point out. We can say that it's 0.00056 multiplied by, and this one's a little bit harder to put all those zeros in. So 0.062, just like they gave it, times 10. Since they said micro, it's going to be -6. So to the -6. This is our variable for our frequency, so our resonance frequency. So FR is equal to 27,010 hertz. We want it in kilohertz, so move that decimal point 1, 2, 3 forward, and we'll just write it as 27,000 hertz. 27 kilohertz. We'll plug that in for our value here. 27. And we'll check it. That's what we wanted. All right, so keep in mind when they say no winding resistance, you can eliminate the top half, replace it with a 1, and get your frequency output. But if they do want winding resistance in parallel, you do need to apply this top half. We'll do that in the labs this week. All right, let us know if you have any questions.